So I wanted to try something new with the risk that, like Dries was saying, it's a completely new thing, which is basically most of the results were obtained on a plane from from Israel to here. So there is a risk that you find it trivial, stupid, and etc., with many disclaimers. And another thing is that there's no real slides. There's only figures, because this is the only thing that I could do on the plane. So what I'm going to do is I'm going to show you some plots, because this I cannot draw. And I'm going to write on the board. So hopefully you understand everything. And let's see how it goes. So this is the disclaimer. Another thing is that there's going to be no citations and references because of obvious reasons. So I'm sorry for anyone who is offended by that. Okay, so this is a work which was done with Jad Halimi, and who is now in LMU, and Achilles Lazaridis, who is now in Zoom, and and in Zoom, and he's listening to us very carefully. He said he's going to look as a hawk, as you see in this picture, to see that I'm not doing any mistakes. So if I fuck up, sorry, pardon my French, you can address the questions to him. So the outline is going to be like this. We are going to start. So Zlatko told me that there was no talks here about the PXP. Okay, so what I'm going to do, since there's about half of you are students, I'm going to introduce the model and the terminologies that I need for the talk. So it's going to be basic. And then I'm going to introduce the new thing, which is a non-Hermitian version of the model. And the idea, basically, the questions that we're going to discuss, I had to start with this, is that can we, so in the PXP, as you will see, there are special states which are called scars. And there's special initial stage which have oscillations or revivals. And the main questions that we want to address, which sounds a bit risky, is this phenomena stable in the presence of a bus, right? So if you attach a bus to the PXP, what happens? And the surprise is that you can have some non-trivial effects. And then we'll summary. Well, the summary is going to be basically what I said just now. Okay, so let's start with the PXP model. So now I'm moving to the board. I need to stop. I need to do some manipulations here so Achilles can see what I'm doing. He cannot complain. So basically, the PXP model is a sum of the following terms, where a xi is the matrix like this, okay, which we many times write it like that. And here I'm using, I think, a little bit slightly different notation from what people use in papers. I don't know why, but this is how I did my numerics. So I'm sorry for this. So this is a projector, which is 0. Okay, so if there is, okay, this is an I is number of up spins. Okay, so if there is an up spin, it is vanishing, and if there is a down spin, then it is is not vanishing. And what is interesting to see about this model? Okay, so first of all, we what? I don't know. I don't want Z. Huh? Sorry for the 1/2. Yes. Okay. Thank you. So now what we notice is that we can write the Hilbert space of the Hilbert space using states which look like that. Okay, so spin up. I'm going to write it actually. So instead of writing something like this, Okay, I'm going to write it in Zlatko notation. So Zlatko is going to be happy with dots and circles. Okay, in this way, I think it's also more visually pleasant. And what is quite easy to notice is that the Hilbert space is fragmented, so it's connected to, in some remote sense, to what Shomi was telling us. And the fragmentation is as following. So any time that you have a state and let's suppose two circles like this or more. Okay, it can be more circles, but more than one, so 2, 3, 4, etc. Then you cannot, writing it down, you cannot remove those islands. Okay, and this is kind of easy to see, so you just apply the Hamiltonian on this state, and you can see that you cannot, okay, so here there is also an open side, you cannot change this part. So as a result, there is a special subspace which I'm going to consider during this talk and which is typically considered in this context. So it is the maximally connected. Actually, want to put it there because I want it to stay. Hopefully the camera can be fast enough. Maximally connected subspace. Okay, so I'm not going to do this for 8 spins, forgive me. But we are going to start with a special state, which is just the nil state, but Zlatko likes to call him Z2. Okay, and there is another state which is going to sit here, which I don't know how Zlatko calls him, but I'm going to call it Z2 bar. Okay, good. Okay, I got the okay. So this guy is like this. Okay, and now what I'm going to do, and this is basically for the students, not the most efficient procedure, but a procedure which is much more efficient than the naive approach, is to construct the graph which goes from here to here. And I'm going to do it by applying the Hamiltonian, the Hamiltonian. So what the Hamiltonian does, I didn't say something very important. I'm going to write it here. The boundary conditions for all this talk is going to be periodic. Okay. So what I'm going to do is when I apply the Hamiltonian every time that there is an open circle like this, it can flip this spin here. Okay, and also this spin can be flipped. So as a result, there could be two possible states. So I can either flip this spin, or I can flip this spin. Okay, so those are the two states. Okay, then now I need to apply the Hamiltonian again. So if I apply the Hamiltonian again, I can go back. Okay, but this is not important for me because I know already the state. Or I can go forward here, and you can easily convince yourselves that the only thing that I can do is to remove this dot and to get the all zero state. Okay, let's write it like this. I don't know if there's a special name for it. And now in the next stage, what I'm doing is I'm going to apply now on this state. I can also apply on this guy, but it's more complicated because one of the times I'm going to go back, and one of the times I'm going to go here. So it's easier to apply on this state. So it's going to be like this. And like this. Okay, so this is the entire connected Hilbert space. I didn't draw the lines which connect the states, but this is it. And now what is going to be important for next is the number of ups Okay, let's write it is the way it's going to appear on the plots. A number of ups, and you can count. So here it is 2, 1 is 0, and then it goes again back to 1, 2. Okay, so the Z2 and Z2 bar are the have the maximal number of ups. Okay, so this is what I want for you to understand right now. And now I need to come back to the presentation.
This simple n up 1, 0, 1, 2, it's only for the size.
Sure, of course. Yeah, sure. It's just an example. I mean, typically what's going to be, if you want the general here, is of course, it's going to be L over 2.
In the middle of the chain, it won't be only 0.
No, in the middle, it is always 0. Here. This one is always in
the middle.
Only 0 in the middle, yes. Okay.
Already from the size 6, it will be this 3, will be there.
Okay, let's discuss. It's not important, Ivan. Let's not discuss.
So it's 0, but with this distance half of the diameter, it's not 0.
Let's say you want to. It's not important. Okay. Even if it is correct, it's not important. So okay, now it is. It's like like a. No, probably I shouldn't say this, but let's go to just share.
Not going good. No.
Why not?
No.
Why I don't see this? Oh no, escalator. What? I'm not in Zoom? No, I'm in Zoom.
You are, but here, are you sharing? Try to share.
This guy.
Yeah.
Okay, good. Okay, so now I am going to do phenomenology. So what is important about this is the so this model. Okay, I'm not saying where it comes from. You can read the Atlas review or the first paper, etc. It comes from a nice experiment. I'm not telling you about this. I'm going to tell the phenomenology which is important for what we do, and this is the following. So what people noticed is that these Z2 and Z2 bar states are special in the sense that if you project them over the eigenstates, so what you see here is just a projection over the eigenstates. So E is the eigenstates, Z2 is the state, and I'm putting it on a log scale. And you see that there is a bunch of states. Let's see if I can use this laser. Yeah. See that there's a bunch of states which has a very high overlap with Z2, and in fact the overlap with other states for those special states which are called scars are negligible. So this is one thing that people noticed, and the next thing is that if you look on the entanglement of those states, it also appears to be low. Okay. So those states that you saw before, so this is just the half-cut entanglement, have an exceptionally low entanglement. So those are the interesting facts. And now what I can do, okay, what I'm going to do, this is just a procedure that's going to be important later. I heuristically put, so Zlatko in his paper is a fancy way to find those scars. I just want a simple-minded way just to separate them, not to really find the values. So I put a threshold. This is just a threshold I put by hand to separate the scars from the rest. And what you see here, so this is a plot of magnetization, of the average magnetization. So this is this guy, but computed now for all the eigenstates of the system. And you see that those states have an exceptionally high magnetization, which of course corresponds to the fact that they have also an exceptionally high overlap with Z2 and Z2 bar. Okay, so it's consistent. So this is another important bit. And now what is interesting is that you also need to notice from this plot or the previous one is that there is an equal energy separation or very close to equal energy separation between those states. What that means? It means that if I start with an initial state which is Z2, okay, it is going to populate those eigenstates here, okay, like mostly. And because they are separated with the same multiples of energy or very close to it, then I expect to see oscillations. Okay, it's going to be a periodic function. So this is indeed what. So this is the important bit which was to explain the experimental results. So in the experiment, they prepared this Z2 state and observed the oscillations. And the paper, Zlatko explains with the co-authors, of course, explains how it works. So, so what you see here is two graphs. One graph is corresponds to the overlap with Z2, and the other one it corresponds to the overlap with Z2 bar. Okay, so now I want to. Okay, Achilles is not going to see this, but it's not important enough to switch. So what happens here is that if you start with this initial state, so the dynamics is that you move through this Hilbert space to the Z bar, and then back, and then you oscillate like this. Okay, so this is how the dynamics goes. You can see it from here, and it's decaying, but very slowly. So this is the overlap. If you look on the spin itself, what the spin does, so since you switch from Z2 to Z2 bar, so if I look, for example, on this spin, okay, so the spin switches from up to down, etc. Also indefinitely. Yes.
What is G?
G, forget about it. Not important right now. It's going to be important later. This is just the PXP model. Okay, so now we are coming to the question. So this is we are done with the introduction, and now I can go back to. No, I cannot go back yet. Are scarce stable in the presence of the bus? So I think people consider this. I don't remember the references, but people connected it, and I think it's also a very natural expectation if you connect the bus to this scar, because you see that there are special states, special initial state. You connect some dissipation, so this thing is going to disappear, and indeed. And indeed, this is what happens. I mean, at least I tried this with naive buses, and it's pretty fast destroys all the phenomenology. But okay, if this would be the case, I wouldn't be telling you the story. So we found a way which we call, this is the GPXP model. It's a really bad name. So if you have a better name, please tell us. So what we are going to, so now I'm going to present the model, and then I'm going to show you the results for it first.
Yeah, okay. Should we?
He knows the model. It's only him. It's only him. It's only him there.
Let's check if it's only him.
Yeah, it's only him.
Okay.
It's not important. I mean, he's going to see what I wrote later. So this model. So now we want to have a non-Hermitian model. Okay. So the way I'm going to do it. I'm going to change this matrix to become non-Hermitian, and the way I'm going to do it is in a gist similar to Hatano-Nelson. Whoever, if you know, if you don't know, you'll see what I do. Okay, so what I do is this guy doesn't change, and now okay, so you know, of course, that. X is sigma plus plus sigma minus. Okay, this is a fact. So what I'm going to do is I'm going to give different rates which depend on this G. To the sigma plus and the sigma minus. And here this P stays. Okay, so this is the model. So this is the model. Now, why we want to think about this model, and I'll try to explain to you why I don't think it is trivial. You can try to explain to me maybe why it is. Hopefully, we'll compromise. But basically, what you see is that there is a difference of rates here. So if G is positive, you preferentially push the spins up, okay, but given the constraint. And if G is negative, you preferentially put the spins down, also given the constraints. Now, what is the problem? The problem is that, well, at least for me, the conceptual, it's not immediately clear what's going on. Is if you start with Z2, I told you that the dynamics for G equal to 0, now you know why it was written G equal to 0, is that it oscillates from Z2 bar and etc. Okay? So the magnetization, if you look here, changes from 2 to 0, like it decreases, increases again, and so on. So what this rate does, it creates some sort of a competition to this dynamics, and therefore it is not immediately clear who wins. Okay? So now I'm going to show you who wins.
Sorry, before I have a general question about the non-Hermitian systems in general. Cioè, when people do open systems, dissipation, like with the Lindbladian, they always have a term that enforces the trace preservation. I mean, the fact that the trace is preserved. Here you explicitly. So how should I think? Because not having
So it's a good question, and there's no very good answer. But so for non-Hermitian systems, there is this problem that, of course, probability is not conserved.
Yeah.
And then what you need to do dynamically, what we are doing, is you need to constantly renormalize the wave function, which is decaying or exploding. Okay? But let's talk about the limits, that this is what you are asking. So there is a limit, which is called the non-clique limit, to derive a non-Hermitian system from a Lindbladian. Unfortunately, this model does not correspond to this limit, which we can discuss later, not now.
Yeah, sure.
Okay.
And vice versa, then I stop.
Yeah.
Do you think one can try to complete the model to restore the trace preservation, or you need to do by brute force?
Maybe there is a way to somehow
embed, like
do something similar with the Lindbladian approach. We don't think yet.
Okay.
There's a question there. Yeah.
Into use one of the products.
That's roughly what's going to happen. Yes, that's roughly. But what I'm trying to say is you can guess this from here. Yes, also because you said skin effects. You are familiar with Haddad and Nelson. But there is a competition. This is what I'm saying, because the dynamics without the G, it tries to go from here to here, and the G actually wants to have a preferred direction. So now it's not clear who is going to win.
So if you want, this will be a skin effect in Hilbert space rather than in physical space.
It is in Hilbert space in some sense, yes. Yeah. Okay, good. So now we can show the results to show that it's interesting. Well, to me, it is interesting. You can periodic always. Okay, numerical results. I'm going to show this and we come back to the board. Okay, so we plug in G equal to 2. And you see that the scars are stabilized. Okay, you see is that there is a very strong tendency to be either at the Z2 or Z2 bar state. It becomes sharper the larger the G is. Okay, and it does not appear to even decay with time. So this is
and this result is obtained okay.
Always renormalizing. So I already answered this, so we keep this in mind. In the dynamics with non-Hermitian Hamiltonians, we must always renormalize. And this happens when the G is negative. So from here, it's not obvious, but you can guess. So the overlap with Z2 just vanishes very, very, very fast. Okay. And if I look on the spin, so again, I look, for example, on this spin. So again, I see the same because the overlap was oscillating. It's also the spin is oscillating quite sharply between -1 to 1. Okay, and for minus G, okay, so here now you have the first clue of what happens. you see that the spin now decays to -1. Okay, and this actually happens to all the spins. Okay, so basically what it means is that we do decay to this state in the middle. Okay, good. So now we can stop the sharing and come to explanation. Yeah, you want to, now's the time to ask about the figures. Because I'm stopping the
because I think I was just guessing.
No, so yes, it's good. I actually want to hear.
No, the issue is that the sectors with more than two particles, they are disconnected, right?
Yes.
So if you try to push up spins, you don't go there.
You cannot, yeah.
Okay,
And that
so
is
you just
very,
go at the
that is
limit.
very important. Like if I wouldn't put the G inside the constraint, it would be completely trivial dynamics.
Yes.
Really, really
Yeah,
boring.
exactly. So, but if you destroy spin, nothing prevents you from destroying
Yes.
everything and going to the zero state.
Yes, exactly. Very good. Okay. So now analytical explanation. We can come back to here. And now Hilas can see what I did. This I can erase. So how do we understand this? Ah, shit, I wanted to show you a plot. Let me first show you the plot. It is important. So it is kind of, well, sort of little bit of luck, I think, that we notice this. But if you plot the eigenvalues, this was like a numerical hint to what to do, okay, analytically. So this is why I'm showing you this first. Is you see that the eigenvalues for g equals 0 and g equals 2 is the same. Now, why we checked? Because we know that the same thing happens in Hatano-Nelson, so it was like a thing. And this connects us in some sense, and maybe even stronger sense that I still understand to Driess's talk, that we understand that the spectrum is the same, and it means that the model or the family of models with G are connected by similarity transformation.
So there is a PT symmetry?
There is not a PT symmetry, there is a similarity transformation which connects the models. Okay? Okay. So now the question is, can we find this similarity transformation? And the answer is, of course, yes. Otherwise, you wouldn't see the next section. It's actually very simple. And this is what I'm going to show you. So after we get the similarity transformation, everything is going to be clear. Okay, good. So let's. Okay, so what I'm going to do, so I'm not going to tell you how we found it because it's just by playing. So it's not, there was no like really deep thinking involved. But basically, I'm going to tell you the transformation and to see how it works. Okay, so I'm going to define the matrix CG, the sigma G, as this matrix here. Okay. This is going to be a sigma G. Okay, and I might get confused with the signs, so I'm sorry in advance if I do this, but then we can just change G to minus G, and everyone are going to be happy. Okay, so this is the matrix, and I want to show you first how to get from this matrix to sigma X with or X, using similarity transformation. Okay, so this is actually very simple. Okay, so the matrix, which I'm going to call UG, which does the trick, and we are going to verify this, is EG1. Okay. What is important to remember about this matrix, I think it will be important in the future, is that it is Hermitian. Okay. It is, however, not unitary. Okay, it is similar. And of course, UG minus 1, since the matrix is diagonal, is this guy. Okay, now it is just, okay, let's do it here, and then, so now we are going to apply UG minus 1 on this matrix. So this is the similarity transformation. Okay. And what we are going to get, hopefully up to the signs, is okay, so minus G. So I'm sorry, I'm doing it slowly, but you're going to be properly convinced that it works. Okay, so I'm copying this matrix first, and we are going to get a 0 here, 1 here, exponent G here, 0 here. Okay, and I'm multiplying this guy again. So this one is going to give me 0. This one is going to give me minus G. Okay, I fucked up the sign. So let's do here it like this. Okay. So the sign is going to be correct. So this is now like that, and this is like this. Okay, so you see that this is indeed a similarity transformation. Okay, now what is good about this similarity transformation is that we now transform just this matrix, but we have those operators. Okay, but why is it a good transformation? It's because it is diagonal in this basis. It is commutes with the p's. And therefore, this similarity transformation is good also for this Hamiltonian. Okay, we did it only for one spin, but you can imagine that I can do it for many. Now, I'm going to write the similarity transformation in a little bit different or more, I think, transparent way. This is good. So I'm going to write it like this. So for many spins, it's going to be like this. And now it is very transparent what it does. Because you immediately see that what it does, it reweights all the states of the Hilbert space here. Okay, we can even do it here now. Okay, so you're going to get 2G here, G here, 1 here, and again G and 2G. Okay, so it reweights all the states with this prefactor. Okay. And now we can actually start, because it is a simple enough transformation, and we can see that. Let me write it in exactly the same way as I did. Where is it? Here. Okay, so I can write it like this. And in order to, so the spectrum is of course identical, and all the eigenvalues. So if this is the eigenvalue of PXP, okay, so the eigenvalues for HG are going to be just, I think with this guy. Okay, so they are going to be just changed by this prefactor. Now note that this doesn't keep the norm of the vector, so you need to, of course, to renormalize. I'm not writing it explicitly here. But the advantage is that now we can really understand how the dynamics evolves. Okay, we can calculate it. Okay, so let's do this. So what we are going to do is we are going to calculate the, so we start with Z2. Okay, we evolved it with, no, what's going on? It was really good. And it died. And this died. Don't worry, there's a blues here. Oh, this is it. So what we want to compute, we want to compute the dynamics of the overlaps like this. So this is the overlaps that we want to compute at the end. But I want to show you something even more general, because we can do it. So why not? So I'm going to write all the product states like this, using Roman letters. Okay, so N or M are product states, and alpha and beta are going to be eigenstates. Eigenstates, but it's important of PXP, of the Hermitian. Okay. And what I'm going to do is I'm going to start with some product state, evolve it with time, and calculate the overlap with another product state. So I'm going to I want to understand everything, like in the Hilbert space. Okay. No, it's this board is killing. No, it was like an amazingly good. Yeah, let's hope that Daria is going to come back before everything dies here. So I'm going to write it down. So we are evolving with HGT, writing it down explicitly, this thing. Okay. And now I'm going to use the similarity transformation. Okay, because you see there is this connection here. And since an exponent is just a function, so I can insert it. So it is going to be, again, to do the signs correctly. Like this. Okay. So this is the evolution of the PXP, right? This is the normal PXP. And now what you need to notice is that the application of UG on M is actually very simple, because it's UG is diagonal, and it's I erased it. Let's put it here. Well, it is written there also, but okay, so it's just sums the number of ups. So you see, when I apply this guy here, it sums the number of ups here for this state, and this sums the number of up of this state, but with a minus sign. So at the end, I'm going to get the difference in big N. Let's call it big. Let's call it big N. I might be wrong with the signs here, but again, it's not important. And here it's going to be just the overlap for the PXP. So this is PXP dynamics. Okay, so you see that for this observable, which is the overlap, the G actually, why beta, G. So the G is actually not doing anything crucial. So it appears, right? But it is doing stuff. Huh? Yeah, but this is on Daria. It's in my advantage, but but it's on Daria. Yeah.
Okay.
Good.
Okay.
Thank you. Okay, now I have a stock. Okay, so I'm going to. So David, do you see? Okay, so this is PXP dynamics here. And what is what is interesting is the following thing. Is first of all, this overlap, the way I computed it here, I didn't include the normalizations that we discussed. Okay, so it's important to remember. Because what we immediately see is if I start with the product state Z2, okay, and I start with Z2 and project on Z2, okay, clearly they have the same number of ups, and this guy dies. So basically, you would expect that nothing will happen with G, but I showed you that stuff do happen, and the reason it is because of the normalization. Okay, so what this term does. Okay, so you start with a Z2, And of course, the dynamics immediately moves you to different number of ups, okay, as we know. But those states, the overlap on those states is going to be exponentially suppressed because of this factor. Because of this factor. And because those states are suppressed, most of the state at the end is going to be on the Z2 and Z2 prime states. And this is how we get what we get, and we don't get upset.
Isn't surprising that because as you said here you are not renormalizing anything,
yes.
But somehow the probability that you lose is time independent, which is
the probability. I mean, you see here only one was overlap on once. Yeah, it is time independent. That's true, but.
Isn't a bit? I would expect that more you wait and more you lose because this doesn't preserve. I would expect something time dependent.
So it is. Yeah, it is. As I said, it appears simple, right? Like, that you go just to this state and you stay there, but I mean this ignores the dynamics, and the dynamics is important. But what this story tells you is the weight, which is time independent, as you said, is reduced. And it means that most of it lies on Z2. So when I take into account normalization is mostly going to be composed from the Z2 state. And this is when I divide one by each other, I get these steps of 1 and 0. Okay, that's basically the entire explanation. Okay, how much we are with time? We're done or what?
As you want.
As I want. Okay. I'm trying to think if I forgot to tell you something here more. That I mean, I think this roughly explains what we are missing is to understand what happens with the scars. Okay, this is so the scars. If you recall, there were two ways to identify, and this is actually kind of cute. Is also to understand, is also to look on what this guy does to the eigenstates, basically, not only to the scars, but to all the eigenstates. So what I'm going to show you now, and you can guess from here, right? You can guess here, so you know that if I take any state in the Hilbert space, so basically I weight according to these weights here, okay? So how to show it? Okay, so what we are going to do is I'm going to project the eigenstates to magnetization sectors. Okay, or specifically, let me write something and write it down before we switch to. So this is, I think, clear. Let's put it here. So basically what I'm saying is if there is a projector on a certain number of n ups, okay, we are going to take the eigenstate and we are going to see what is the weight. Okay, I'm going to show you the distribution of it. Okay, I'm not sure if people did this. I mean, it was curious to, I mean, it's not very profound idea, but for this, it's actually very helpful. Okay, yes. Good. So, wait a second. So, okay, I wanted to show you first other stuff. Okay. So this, you can see what the weights do to the eigenstates also by looking on the average and up, okay? So here you see a plot of the expectation, right, of an up for all the eigenstates. And it is actually pretty nice because I didn't put the g equals 0. So if you plot the g equals 0, they're not so nicely separated. But if you plug in a finite g, there's a very nice separation from the scars. I think it's very apparent. It's not a big system size. As I told you, it's I think half of the system size as Zlatko is doing. So it's pretty much bad, but it's still sufficiently good to see what happens. And this is for negative G, which is I think even more interesting. We are going to come back to it later. So there is a separation between low-lying states and there appears to be like almost a gap between the other states. And now we are coming to the more interesting things which connected with the weight. Okay, so I actually don't see the G equal to 0. So this is annoying, but so this is already a finite G result. So what I did is I separated the states using this, I don't know if you remember this simple-minded parabola which I drew between the scarce and not scarce. And I calculated this weight, so this weight here, so this is what is plotted, P, how did I write it, N of up. Okay, so I calculated this weight for the scarce on the left and the non-scarce. So for some reason I don't see the plot here for G equals 0. It would be actually, yeah, I didn't put it. But what happens for G equal to 0? Maybe I'll draw it here. Hiles will forgive me. He didn't see this plot. So for scarce, so this is the P for the peaks P, right? So for scarce, what you see and you can see that the weights go from 0 to L over so 0 and to L over 2. Okay, so this is the weights. And for scarce, what you see, let's do it with colors. So for scarce, what you see is something like this. Okay, so the scars are here. There is some dependence where the scar is sitting. Okay, so the scars which are closer to the edge of the spectrum, they're having a little bit closer, they start moving to the middle here. But what is interesting is that the thermal states are sitting very nicely here in the Gaussian in the middle. Okay, so there is a dramatic difference in terms of the distribution. You cannot get confused, even for such a small system size. Okay, and now what you see for a finite G, so what the finite G does? So a finite G just takes those graphs and applies an exponent to it. So let's draw it with blue. Okay, so if you have an increasing exponent, it's going to be like this. So we are weighting those weights with this exponent. And okay, I don't have another color, but you can imagine that with a negative G, it's just going to be decreasing exponent. Okay, now you see the effect of it. Okay, this multiplication, it's simple. Of the function, you see that the scars are pushed very strongly to the Z2 state. Okay, so they have almost all of the weight on the Z2. But it also happens to the other states. Also, the thermal states are now pushed from this Gaussian, which is sitting in the middle, to closer to the edge. Okay? And if I do it with a negative G, it is, of course, goes to the other direction. Okay, so now we understand how the weights changes. And one thing which is missing is what happens to the entanglement entropy. So this we cannot compute analytically. I mean, I don't know how to. So we have, this state. This is the new state, and we need to see what's happening to its entanglement entropy. The guess is, what is the guess? The guess is that you saw what happens to the weight. You are pushed towards basically product states. Either for positive G or negative G, you are pushed to here, but you are pushed to product states. So the intuition is that the entanglement entropy is going to decrease. And this is indeed what happens. I'm not going to show you in contrast, but I am. So this is G equal to 0. And this is G equal to, it's the same scale, so you can see the effect. Okay, but look now on the scar state. So this is this arc of states which flow entanglement. But look what happens for finite G. They sit on a line. Okay, it's a stupid line. If you see it's 1, and we are counting it in log 2. So it means, okay, one product state it is. Okay, but it's really nice because you can really easily separate them now because of this line. And for G minus, it's actually more interesting And I cannot tell you that I understand this plot, so I'm going to tell only the bits that I understand, and I'm happy to have ideas. So you have two interesting things here which are visible to the eye. One thing is that there are states with zero entanglement entropy. This is easy to understand. Okay? So why is it easy to understand? Those are states where you reduced to really one product states. So before, I need to fix myself in the previous explanation. Before we had, in this graph here, we had two states, right? This is why it is 1 bit, right? We had two states, Z2 and Z bar. So entanglement was 1. Here we have only one state, all zeros. So this is why entanglement is strictly 0. Now, why there is this family of states which have entanglement 0 strictly and entanglement which is not? This is also easy to explain. Why? Because for this model, not all eigenstates have overlap with all zeros. Okay, some of them have not, and the reason is just symmetry. Okay, so the model is translationally invariant, and the all zero states corresponds to k equal to 0. Okay, and parity positive. Okay, so those states have the 0, and all the rest don't. Okay. And therefore, the states that sit in the bottom, they are just those states with k equals 0 and positive parity. I didn't separate the sectors in a fancy way. This is why I'm restricted to this a small system size. What I don't understand right now is why there's this gap. Okay, so there's a gap, clearly. I do understand the separation of the families, but I don't understand why there's a gap, which appears to, I mean, there are some violations of the gap, but appears to that there is a lot of states with entanglement of 1, namely corresponding to 2 product states. Not obvious. I try to look on the...
Isn't because, let's say, there is only one state that come in a single, which is a singlet, which is 0. All the others come at least in pairs, so they must be at 1 or higher.
So I don't know why they come in pairs. That's why. That's the thing.
Because they are paired by e to the g. So either, let's say, you have 0 and then you have 1, 1, 2, 2. So if you... Right.
So
okay.
it is, but it must have to be something with pairs, but I don't know right now the explanation. Just because I plotted this graph about 48 hours ago. Okay, but we'll figure it out. If you have ideas, come and tell me. But our guess, it has to do with symmetry. So as you said, the pairs, what we know is that, for example, for k's which are not equal to 0, the states are degenerate. For not 0 and not pi, the states are actually degenerate.
And you know that the scars are all k equal to 0? No, or they could be scars that are in 1.
They can be others. That's a different work that at some point we'll wrap up. I think I'm quite done. So I'm also probably heavily over time, no?
Well.
But anyway, I mean, that's my point. I don't have, if you have any suggestions of additional points, but the point is that the dissipation can actually work to stabilize the scar and not only to destroy them. How to make it physical and stuff like that, maybe the additional things to think about. Yeah, I'm done.
I have a lot of questions, but let me ask only 2 for a moment. So first of all, so as soon as you go to the non-Hermitian system, you have left and right eigenvectors. What you showed us was only for, say, left ones? Entanglement entropy, everything?
You mean like the entanglement entropy?
Yes.
It's the right ones, I think.
Only right ones. So, and do you know the difference in statistics?
It's the same because it is, you see, I mean, the left ones is going to be just with UG instead of UG minus 1. So it's going to be roughly the same, just the sign of G is going to be reversed.
But sign of G is very important for you.
Yeah, it's important, but we know what's going to happen. Okay. Right? Like, I know what's, I mean, I showed you the plots. So this is G positive, this is G negative. They're going to be reversed.
So it's for dynamics for one of them will be really like stabilized, for another destroyed completely. What is the physical dynamics? right to left?
Well, the physical dynamics, it's what you calculate, and then you don't care about eigenvalues for physical dynamics. You care about those guys. Well, this is also presumably not really physical, but you care about expectations with operator and stuff like this. So you can calculate this, and this, I know how it depends on G.
Maybe the second question, because I asked it in the very beginning, like if you consider larger system size on the equator between Z2 and Z2 bar, there are Z3 states also. Have you tried to check whether you suppress them in both cases?
Think about it. It's like in even odd effect you're talking about? Or
No, Z3, it's like every third is occupied.
You mean like in between there?
Like they are living in the Hamming distance, they are living also at the equator as 0, 1, but they are Z3,
No,
not Z2.
That's the only thing.
Because-
What I showed you is the only thing that we tried.
Probably both, they will be suppressed both
So
for
there's
positive and
nothing
negative J.
hidden. I told you everything, all the calculations, everything is in front of you.
More questions? Okay,
Okay,
if
that's
not,
good.
we can thank the speaker again.
Good.